Hi everyone, welcome to Production ML Papers to Know. In this series, we'll give you an overview of some of the most important papers to know if you're building machine learning powered products, from the classics to the new and promising. And this week is our first edition of this series, so I thought we'd cover one of the all-time classics, the high interest credit card of technical debt paper. Imagine it's 2014. The AI hype is starting to heat up. Google is paying what seems to be crazy amounts of money for this weird research startup called DeepMind, and talks of a deep learning talent war are already starting to begin. Now, Facebook and Microsoft are launching these attention-grabbing product features that are powered by this new technology, and the rest of the world, tiny startups to large enterprise companies, are starting to perk up their ears. And it's all hope and upside at this point, right? MLOps is just a twinkle in the eyes of an enterprise product marketing executive. But now imagine that you're one of the people that's actually been doing this for years. So what do? You write a paper highlighting the very real trade-offs that you'll face when you do get to the point of actually building a product using this new technology. And that's the amazing thing about this paper to me, is it was so ahead of its time. So few people were actually building with ML at this time, and the conversation around production ML was pretty much non-existent. Yet this paper highlights challenges that still ring true to this day. So let's dive into it. The core idea of this paper is that with machine learning, you're getting this really powerful technology, but that power doesn't come for free. It also introduces new kinds of technical debt. What is technical debt? When we move fast in an engineering organization, we implicitly or explicitly make trade-offs between the speed that we're moving and the quality of execution. And technical debt is a way of quantifying those trade-offs. Now, technical debt is not necessarily bad. Sometimes these trade-offs are the right ones to make, but it does tend to compound over time. So it's worth understanding the different types of technical debts that we might incur so we can deal with them better later. One of the main observations made in this paper is that the unique aspects of model development tend to encourage poor software engineering practices in general, from glue code to jungles of data pipelines that you might build. But I don't want to focus on this part of it, because I think the more interesting part of this paper is that it introduces new kinds of technical debt altogether. These are the three that the authors observe, and let's dig into each one of these separately. The first is boundary erosion. To understand why boundary erosion is a problem with ML systems, we first need to understand encapsulation in software design in general. Encapsulation is the principle that your software should really tightly couple the data that you're operating on with the methods that operate on that data. So for example, let's say that you're building a software for a bank, and you might have a concept of an account and a bunch of manipulations that are associated with that, like making a deposit or making a withdrawal. A design that uses encapsulation would expose just those manipulations that you deem necessary to the outside world. Other parts of the system can't make arbitrary changes to the account. And this allows you to really effectively break the system into components, and to know that the logical consistency of those components won't be broken by other components, which is great for things like testability and maintainability of each component. But one of the things this paper points out is that in machine learning, these systems don't tend to lend themselves well to encapsulation. And they articulate the reason why is that changing anything changes everything. If you add or remove a feature to your model, if you change a distribution of a feature or change a hyperparameter, you can't really isolate the effects of those changes. They might change the meaning of every single other feature and your performance across any different slice that you might care about. So this is one really big challenge. Another reason machine learning systems are prone to violations of encapsulation is that they're subject to these hidden feedback loops. Let's say that you are deploying a recommender system and you make a change to the predictions you're making to your users. That will lead to a change in your user behavior, like maybe they'll click more on a certain category of item that you're recommending more. But unfortunately, that will lead to you collecting different data going forward, because you only have the data about, let's say, the items that the user does interact with. And so that when you retrain your model, that'll feed back and change your model going forward. And so it's really hard to reason about the system in isolation when behavior drifts over time with the real world. So that's violations of encapsulation. The second form of technical debt that the authors introduce is expensive data dependencies. And they give a few examples of this. Data that's consumed from other systems. So let's say that you're building a machine learning model on top of a feature, but you didn't design that feature, another team designed that feature. Or potentially even you're consuming the output of another model as an input to your model. Like let's say that your model consumes an embedding in order to use that embedding to predict something about how your users will behave. Now, the problem with these data dependencies is that they tend to be very unstable, much more so potentially than the code dependencies that are analogous to them. And these are made even worse when these dependencies were never really needed to begin with, right? If you're using a particular feature that is superfluous. The third category of forms of technical debt that are introduced by machine learning systems is difficulty dealing with a non-static world. The real world tends to change, and a common observation that people make about production machine learning systems is that if your data distribution changes, that means that your model might no longer be valid. It violates the IID assumption, which is core to how we build machine learning models. But the authors point out a couple of more subtle implications of non-stationarity that I think are worth pointing out. It's not just about changing feature distributions. A lot of times when you deploy a model into the real world, the raw prediction of that model, let's say the score that the model produces, in order for that to be translated into an action, to an outcome that happens to the user, you wrap those scores or those raw predictions in rules. Predictions above this certain threshold are going to be classified as positive. Changing domains, changing distributions can affect not just the distribution of features, but also the meaning, the correct usage of those rules, as well as correlations between features, right? So it's not just enough to look at individual feature values. Wrapping up, what does this paper tell us? I think kind of the main lesson to take away from this paper is that with great power comes with great responsibility. Machine learning introduces all kinds of new technical debt, and it's really caused by two factors. Right. So one is one of the benefits of machine learning, which is that models are not hand engineered, which means that it's very difficult to understand how the different pieces reason and fit together. And on top of that, like one of the other benefits of machine learning is that it's derived and it can influence real world data. But that also introduces new types of technical debt that you have to deal with. The authors do also go on to talk about a few mitigations that you can use, and most of these have to do with tooling. This is one of the earliest and most classic papers in production ML, and I think it's still very relevant today. My one wish here is that the authors maybe went deeper into examples that they'd seen and potentially some of the mitigations that work well for them. So that's a quick summary of the hidden technical debt paper. Would love to hear what you think. Feel free to leave a comment with your takeaways from this paper, or if there's any other papers you'd like us to cover. See you next time.